In this episode, we're going to focus on what happens when automation starts confidently and then suddenly falls over halfway through, which is one of the most common and most stressful failure modes for beginners. A runtime error is different from a syntax error because the code was valid enough to run, and it is different from an undefined variable error because the system already had the information it needed to begin. Instead, runtime errors happen when the automation collides with reality, meaning the environment is not in the state the automation expected, a dependency is unavailable, a permission is missing, a resource is busy, or a timing assumption turns out to be wrong. The hardest part emotionally is that you can see that some steps worked, so it feels like you are in a half-built world with no clear way forward. The good news is that runtime troubleshooting can be extremely systematic because the environment gives you clues if you know how to read them. The goal is to replace panic with a repeatable method that helps you find the real root cause and decide the safest next move. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. The first mental shift is to treat a mid-run failure as a snapshot in time rather than as a single mysterious event. Your automation had an intended path. It executed a sequence of actions, and at one specific point it stopped because something became false, unavailable, or invalid. That means there is always a boundary between the last successful step and the first failing step, and that boundary is where you begin. Instead of asking why did it fail in general, you ask what exactly was the last thing that succeeded and what was the next thing it tried to do. This is a powerful framing because it turns the problem into a narrow investigation, not an open-ended search. Once you identify that boundary, you can collect evidence about the system state at that moment, such as whether a resource exists, whether it is ready, whether it is reachable, and whether the automation identity has the rights it needs. Mid-run failures often feel random, but they are usually deterministic when you account for timing, dependencies, and state transitions. A systematic approach starts with classification because different classes of runtime errors point to different kinds of fixes. Some runtime errors are about connectivity, like not being able to reach a service, endpoint, or host. Some are about authorization, like being denied access to read or change something. Some are about conflicts, like trying to create a thing that already exists or trying to change a thing that is currently locked or busy. Some are about invalid inputs, like sending values that violate constraints or referencing a resource that was never created. Some are about time, like an operation that has not finished yet when the next step begins. You do not need to memorize categories, but you do need to recognize that each category has a predictable investigation path. When you classify first, you avoid guessing and you avoid wasting time trying fixes that do not match the failure type. After classification, the next habit is to capture the evidence in a way that preserves context. Beginners often rerun immediately, and sometimes that clears the issue, but it also destroys the evidence of what happened the first time. A better approach is to pause and record the failing step, the exact error message, and any identifiers involved, such as the name of a resource, the operation attempted, or the response code from an external service. This is not about paperwork. It is about making sure you are debugging the real event, not an altered second attempt. Mid-run failures can be caused by transient issues, and if the second run succeeds, you still want to understand why the first run failed so you can prevent it in the future. If the second run fails differently, you want to know whether the environment changed because of partial success, which can complicate recovery. Evidence preservation keeps your troubleshooting grounded and stops your brain from inventing stories about what might have happened. Now focus on the environment state, because runtime errors are often a mismatch between expected and actual state. Your automation expected a resource to exist, but it does not. Or it expected a resource to be absent, but it is already there. Or it expected a service to be ready, but it is still initializing. Or it expected credentials to have access, but access was revoked or never granted. When you approach this systematically, you explicitly state the preconditions for the failing step and then verify them one by one. Preconditions include things like network reachability, name resolution, required permissions, existence of dependencies, correct configuration values, and readiness of components. The strongest troubleshooters do not start by changing code. They start by validating preconditions. If a precondition is false, you have identified a concrete cause that can be corrected, either by fixing the environment or by adjusting the automation to handle that condition more gracefully. Timing and readiness are especially important in mid-run failures because automation often moves faster than real systems can stabilize. A resource might be created quickly but not become usable immediately, which means the next step can fail even though the earlier step succeeded. This is common whenever systems have asynchronous operations, background provisioning, or eventual consistency, where changes take time to propagate. The systematic way to handle this is to identify which steps depend on readiness and which signals indicate readiness, such as a service responding, a resource reporting a stable status, or a dependency being reachable. If your automation assumes immediate readiness, it may fail intermittently, which is the worst kind of failure for confidence. When you see a failure that disappears on a rerun, treat that as a strong hint that timing is involved, not as proof that the problem was imaginary. Operationally, you want automation to be calm under timing uncertainty, which means it should wait for readiness or detect when it is too early to proceed. Permissions are another frequent root cause, and they often show up only at runtime because the automation cannot know what it is allowed to do until it tries. A mid-run permission failure might mean the automation identity lacks a specific right for a particular operation, or it might mean the target system is enforcing a policy you did not anticipate. The systematic approach is to confirm what identity the automation is using, what scope that identity has, and what operation was denied. It also helps to verify whether earlier steps used different permissions, because sometimes a run starts with one identity and later calls a component that uses a different identity. Beginners sometimes respond by broadening permissions as a quick fix, but operationally that is risky and often unnecessary. A safer mindset is to grant the smallest additional permission that makes the failing operation succeed and to document why it is needed. When you troubleshoot permissions this way, you improve reliability without quietly weakening your security posture. Conflicts and locks are another class of runtime error that can make automation feel like it is fighting the environment. A conflict can happen if the automation tries to create something that already exists, update something that was changed by another process, or modify something that is temporarily locked. In mid-run scenarios, conflicts are often caused by partial runs, parallel runs, or manual changes happening in the same environment. The systematic approach is to determine whether the conflict is about duplication, concurrency, or state divergence. If it is duplication, the key is to decide whether the existing object is the correct one and the automation should adopt it, or whether it is a leftover and should be cleaned up. If it is concurrency, the key is to determine whether another run is in progress or whether a system has an internal lock that needs time to release. If it is divergence, the key is to reconcile which state is correct and adjust the automation to converge toward it rather than blindly applying changes. These steps prevent a common beginner mistake, which is deleting things impulsively to make the error go away without understanding what those things were. Input and data shape problems can also cause mid-run failures, especially when the automation is pulling information from external sources. A value might be missing, formatted incorrectly, or outside allowed limits, and the system rejects it only at the moment it is used. Systematic troubleshooting here means confirming what input the automation actually used, not what you intended it to use. That includes verifying values after substitutions, templates, and defaults have been applied, because a safe-looking definition can turn into a dangerous value once variables resolve. Another part of data shape troubleshooting is confirming that objects have the fields you assume they have, because missing subfields can look like runtime errors even when the top-level object exists. Beginners often chase these errors by changing random parts of the automation, but the faster path is to identify the exact rejected value and then trace it back to its origin. Once you know where the bad value came from, you can correct the source or add validation that catches it earlier. A key part of systematic runtime troubleshooting is deciding whether to rerun, roll back, or repair before rerunning. If the run stopped midway, the environment might be in an intermediate state, and a rerun could be safe or could compound the issue depending on how idempotent the automation is. The discipline method is to identify what was already applied and whether reapplying it would be harmless, which is why idempotency matters so much. If the automation is designed to converge and to avoid duplicate side effects, reruns are often the right first move after correcting the root cause. If the automation is step-based and not safe to repeat, you might need a repair step to bring the environment back to a known baseline before rerunning. Either way, you make the decision based on evidence about current state, not based on frustration. Operationally, safe recovery depends on understanding the difference between a clean rerun and a rerun on top of a half-applied change. You also want to learn the difference between symptom fixes and root cause fixes because runtime errors often tempt you into quick patches. If a network call times out once, the symptom fix is to rerun and hope it works, while the root cause fix might be to handle retries, verify dependency health, or reduce timing assumptions. If a permission is denied, the symptom fix is to grant broad access, while the root cause fix is to grant the specific needed right and verify identity usage. If a resource is not ready, the symptom fix is to rerun later, while the root cause fix is to incorporate readiness checks or a safe waiting mechanism. When you fix the root cause, you reduce the chance that the same error will recur under load, during an incident, or during a change window. That's what systematic troubleshooting buys you. Not just getting past today's failure, but making tomorrow's run less likely to fail. Over time, this creates automation that teams trust, which is the real operational goal. To close, mid-run runtime errors stop feeling random when you treat them as a boundary problem with evidence, categories, and preconditions. You capture what failed and where, classify the failure type, and verify the environment conditions that the failing step depends on. You pay special attention to timing, permissions, conflicts, and input values because those are common sources of surprise in real systems. You decide on rerun versus repair based on how safe the automation is to repeat and what state the environment is in right now. Then you aim for root cause fixes that make future runs more predictable, not just quick patches that get you through once. When you troubleshoot runtime errors systematically, you turn automation failures into feedback that strengthens your automation and your operational instincts at the same time. That is how you move from feeling stuck mid-run to feeling in control of the process, even when the environment is imperfect and the stakes are real.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.